The Brandon Best Podcast. Episode 5. Neuralink Launch Event Commentary Part 2. Follow on Instagram or Twitter at The Brandon M. Best for updates, to give feedback, and to get involved in the conversation.
Okay, welcome back everyone. Time for part 2 of the Neuralink launch event commentary. I'm going to be starting the video here at the 35-minute mark. So I believe they're bringing on one of their head neuroscientists or neurosurgeons. I can't remember exactly what his title is. And I think he's going to start explaining. They're going to be going more in depth on the kind of science part and the R&D part of how they did the N1 chip. And so I'll be doing my regular commentary on that as we go through. So again, it's the 35-minute mark.
Thanks, Max. I'm Dr. Matthew Macdougall. I'm head neurosurgeon at Neuralink.
Okay, neurosurgeon.
When I'm not at Neuralink, I'm a brain and spine surgeon here in San Francisco at CPMC, California Pacific Medical Center. Before that, I was at Stanford, where I worked in labs that implanted and designed advanced brain-computer interfaces. I originally became a neurosurgeon because I wanted to help people live happier, healthier, longer lives. I've been humbled in practice by how powerless we are to treat many of the most debilitating neurologic diseases. People afflicted with spinal cord injury, schizophrenia, autism, and a host of other neurologic conditions have far too few options. I work with Neuralink because we, for the first time in history, have the potential to solve some of these problems. Before we get to how we get the device in, we have to talk about our guiding principle at Neuralink. It's safety. Everything we do at Neuralink is filtered through the question, will this make me more likely to want to get one? Will it make me more likely to recommend this to my family and friends? This approach impacts every design decision we make. So while for the immediate future, Neuralink's devices will only be intended for patients with serious, unmet medical needs, our design philosophy is that this should be safe enough that it can be an elective procedure. So what have we done to try to make it safe? For starters, we've created very small threads. They displace a lot less tissue than the traditional methods. In my regular practice today, I routinely implant large, deep brain stimulator electrodes into the brains of my patients. They're big enough to have about a 1 in 100 chance of causing a significant hemorrhage. They displace and disrupt enough brain tissue that you can often see neurologic consequences just from placing the wire.
So right now he's got a slide up that does a size comparison of the circumference that a deep brain stimulation lead would do, which is what he's saying that he usually does compared to the Neuralink. And so they're just two circles side by side on the screen, and the Neuralink one is probably like 1%, even less, probably less than 1% of what makes up the other one. It's like way smaller. So obviously a huge jump in how much displacement of brain matter is actually going to be done if getting it put in.
We can do better than that. Neuralink's threads are so thin that they're difficult to see with the naked eye. They're much smaller than the width of a human hair. They're small enough that a human surgeon can't actually implant them without help. So we created help. Neuralink developed a tool that we're extremely proud of, the Robotic Inserter. Inspired by designs conceived of in labs here in the Bay at UCSF and Berkeley, we developed this robot that can rapidly and precisely insert hundreds of individual threads representing thousands of distinct electrodes into the cortex in less than an hour. This tool allows a surgeon to aim between the blood vessels that cover the surface of the brain with micron scale precision. The region of the brain shown in this video represents only a few millimeters of surface of the brain.
So right now he's got a couple images up that's showing essentially what the robot is seeing, and you can see the individual blood cells in just a little tiny piece of the brain, like you said, just about millimeters in like dimensions of surface area. And it's there is one of the screens where it looks like someone maybe with a mouse is clicking on points of the image where to actually insert the electrodes. I think I'm assuming that one of the surgeon or really technician, since they want it to be something like LASIK, you don't even need a real doctor to do it. Will actually just on a screen pinpoint all the spots on where to insert the electrodes, and then the robot just does it. So he's just showing up a picture of really the magnification power of the robot they built.
As you can see, the brain's surface moves with the heartbeat and breathing. The robot tracks and adjusts for this movement. Using this tool, we can greatly reduce the risk of harming cortical vessels and causing bleeding. Here, the robot is selecting individual electrode threads and placing them into the brain in the pre-planned location with remarkable accuracy and repeatability. Using this system, we've been able to rapidly place thousands of electrodes into the cortex without causing noticeable bleeding. We also have an in-house histology team that examines brain tissue to help us choose electrode profiles and materials to help us minimize tissue damage. When you think of traditional neurosurgery, you probably think of something very invasive. Traditional surgery on the brain isn't something that patients ever look forward to or are excited about, except in the most dire circumstances. Usually a clamp is attached to the skull to keep it rigidly immobilized to the operating table. We often shave all or most of the patient's hair. Patients can end up with large visible scars. At Neuralink, we want to create an entirely different patient experience, something more like LASIK. No scars, no big scars, no hospital stays, no short procedures, no hospital stays, very short procedures, and of course, in the end, you get to keep all your hair. We even want this to be possible under conscious sedation. That means you can get rid of the complexity and the risk of general anesthesia, as well as many of the unpleasant side effects, nausea, sore throat from a breathing tube. To be absolutely clear, our first clinical trial patients are going to receive an experience much more like traditional neurosurgery. But our aim is to simplify the procedure, down to the injection of local anesthetic, a very small opening in the skin, a painless opening in the skull below, quick and precise placement of threads into the cortex, and then we fill that hole in the skull with the sensor, allowing the scalp to be closed up over it. Behind the ear, we'll make a small incision to insert the coil. We will tunnel tiny wires under the scalp to connect the sensors to the coil. That's the process.
So right now, the image he's showing is essentially there's 4 tiny little holes in this person's skull, and each one has kind of underneath the skin, but on top of the skull bone, there's almost like a flat little bracket that's like screwed to the skull, and underneath that, going down through the rest of the hole to the actual brain matter is all the electrodes that the robot would have threaded. And then there is a thread on top of that little plate that goes down under the skin to, like he said, behind the ear. And it looks like just a kind of like an oval type plate. He called it a circuit. They call it a circuit or thread circuit, but it actually is, it seems like there's a plate with basically a loop of threading on it. And then that is basically right behind your ear. And then the pod, which you take and does like the Bluetooth, I believe has like a magnetic connection to that. So you basically clip it behind your ear and turn on, and then I guess you connect to devices. I believe that's the plan, or at least the design at that time.
I believe that Neuralink is going to be able to provide us in the medical community with a platform that can finally enable us to treat some of these very difficult to treat diseases, also to understand them better. I hope you find this as exciting as I find it. If you feel you might be able to help us, don't hesitate to contact us. To talk more about the technology behind all this, I'd like to introduce Vanessa Tolosa, Director of our Neural Interfaces Group.
Hi, I'm Vanessa Tolosa. I lead the Neural Interface Group at Neuralink. Our team consists of engineers and material scientists who are responsible for making the probes that get implanted into tissue, the packaging for the electronics, and integrating these two components together. We also do all the testing and characterization of these parts. Before joining Neuralink, I led a neurotech team at Lawrence Livermore National Lab. There we worked on a wide range of neuroprosthetic technologies that were used both in the academic and clinical settings. I decided to join Neuralink because I saw an opportunity to take all of this exciting work that we were seeing in neurotech research and actually make them accessible to patients at a much faster time rate than what medical device companies have traditionally been able to do. With that in mind, at Neuralink, we set out to create a fully implantable neural interface with thousands of channels that are capable of single spike resolution. This device must last a long time in the body.
So I think what she means by single spike resolution that I think they touched upon in part one of this kind of little series was being able to read a electrical spike in a single neuron. So that's just kind of the level of accuracy they're actually going for. And usually research EEG headsets, mind you, they're non-invasive, so on top of the skull bone are like, I think 64, maybe 120 channels. I think you can get one in like the 300, so like 360 channels. So having something that's like thousands of channels is massively more, massively better in terms of resolution. So that's kind of what makes this so exciting, and to be able to actually package that really small is what they're doing that has yet to be done. So she has a slide up right now that has some main principles of when it comes to the interfaces, and she's the lead for that. So small and flexible, airtight packaging, stimulation friendly, scalable, and long lasting.
To do this, it must be small, flexible, and made of biocompatible materials that will minimize the brain's immune response. To protect the electronics from the caustic environment of the body, it must have airtight packaging, also known as hermetic packaging. The device must also be able to both record from and stimulate neurons. This is essential for a highly functioning BMI. Finally, the manufacturing process must be scalable and capable of making micrometer-sized features consistently. Currently, there are no research or commercial devices that meet all of our requirements. So we built one out of microfabricated thin film polymers. Just like in semiconductor chip manufacturing, we use a layer-by-layer process that generally consists of 3 repeating steps. We're either always depositing material, patterning a material through photolithography, or etching away a material. Depending on the complexity of the design, these steps could be repeated over 100 times. And to make things more challenging, we are limited to materials that are safe for the body. In our current design, we have a 3-metal layer process that results in a 5-micron thick and 10 to 40 micron wide probe. To give you an idea of how small this is, red blood cells have a diameter of about 8 microns. And an average strand of hair is about 100 microns. Yet in this small footprint, we're able to fit our electrodes, our wires, and the insulation for each of those wires. With microfabrication, we can drive features down to the size of an electron beam. So this is great because we want to make our probes as small as possible. Essentially, we want it to be invisible to the brain. But there are other factors that limit the size of our probes. For example, as we make the wires smaller, it increases the resistance of those wires. And as the resistance increases, it makes it more difficult for us to separate our signals from our noise. Similarly, there are other technical challenges and trade-offs that are related to higher channel counts and manufacturing yield, electrode size, and material and tissue safety. At Neuralink, we have an incredible team that's been tackling these challenges and have been able to make high channel count polymer probes. And this image is a silicon wafer that holds 10 of these arrays, these polymer arrays. In this design, each of those arrays has over 3,000 channels. So what that means is in this one wafer, we've manufactured over 30,000 electrodes and over 30,000 insulated wires. This is something that can't be done with the way current medical devices are being made. That rainbow effect is caused by the small feature sizes on these devices that are interacting with the nanometer size wavelengths of light that are reflecting off of them. If you were to zoom in on the ends of one of these arrays, you'll see this region where we put all of our electrodes. So each of these vertical filaments that end in a loop is what we refer to as a thread. And each of these threads can be placed independently into the brain using our robot during surgery. This design is called Linear Edge. It's one of over 20 designs that we've made for our R&D work. We've progressively been increasing the number of electrodes per thread without significantly increasing the width of each of these threads at the base. We've been able to do this by adding layers and reducing the sizes of the wires down to as small as 350 nanometers. This is less than the wavelength of visible light. Because we're using a lithographic process, essentially if we can draw it, we can also make it.
So right now on the screen, they have kind of their iterations that they went through of thread designs. So the first one, they're kind of vertically stacked on top of each other. And then the next one, even more so vertically stacked, kind of, it kind of looks like a bunch of beads on a thread, if you want to imagine that. And then they were able to up that towards, it looks almost kind of like a tree. So if you have the main stem, and then there's kind of a branch that goes downward and slanted along the main stem and has electrodes on the end, that seem to increase the number of electrodes they could actually fit on there. So there's like a ton of design iterations that they do to actually get to this point over these 2 years. It's not just like they know exactly the design for the electrodes and the threads and all that right off the bat, and they can just figure it out. Like it seems to be a really rigorous iterative process in order to get to, something that looks like it's going to work. And they still, yet it's kind of the best they have, but there's no guarantee that it's probably not going to stay as they've designed it at this time. It might have actually already changed since this event was launched. And that's the case with most physical products, especially like tech products, whether it's software or hardware. It's always goes through a bunch of rapid iterations. So it's just I think what's makes it such a marvel for this is it's something that's never been done before, and it's so far ahead of what the best thing out there was before this. So I think that's why everyone's so kind of impressed and excited about what they're doing.
So on one end of our probes are the electrodes. On the other end are where we connect the probes to the electronic package, or to the electronics through conductive feed-throughs. This substrate is part of the hermetic electronics package. Standard methods of connecting the probes to the electronics package usually involve some kind of large plug-in type connector or a polymer-based glue that bonds the two components together. But as we increase density and decrease the footprint, it becomes impossible to achieve hermeticity in standard medical device connectors. This is due to several reasons. One of them is how these substrates are currently manufactured. Hermetic feed-throughs consist of holes that have been packed with conductive materials and are embedded in an insulating substrate. As you drill more holes and pack them more tightly together, these brittle substrates, typically made of ceramics, become more susceptible to cracking. Also, as you make the holes smaller, it becomes more difficult to fill them with this conductive material without getting non-hermetic voids. Standard processing also requires exposure to high temperatures, typically over 700 degrees Celsius. At these high temperatures, the coefficient of thermal expansion, or CTE mismatch, between the insulator and the conductor can cause circumferential cracking or interfacial gaps during the cooling phase. We're able to get around these problems by developing a new process. So rather than making the probes and then the substrates and then connecting them together, instead we microfabricate them together into one monolithic component. This provides a tight seal at densities that current methods with standard materials for medical devices can't achieve. So far, we've used this process to make a hermetic thin film substrate with over 1,000 connections over a 2.4 millimeter by 2.4 millimeter footprint. Next, we assemble the electronics and then also attach a wired lid using a laser welding process. These two steps have required a lot of internal development as well. The result is the sensor that's ready for final assembly and implants into the body. Next, you'll hear from my colleague DJ about our custom electronics.
Okay, so that whole last segment was just talking about the packaging that the chip sits in. So when she says hermetic packaging, I guess that's referring to an airtight seal. It's like just a little, just like a little cube, not really cube, more flat, but it basically holds the chip, the actual electronic piece, inside of this substrate, this kind of substance that protects it. And then that is basically what sits in, I believe, the plate that's screwed to the skull bone, and then the threads all come out of the bottom. That's what all that last part was basically about. So now I guess the next speaker is going to talk about their custom electronics, which I think this is about the chip itself, rather than the last part was more kind of the biomedical engineering component, making sure everything is safe to be basically in your body.
Thank you, Vanessa. My name is DJ Saw, and I'm the Director of Implant Systems at Neuralink. My team focuses on building chips and systems to get neural signals recorded from our electrodes out of the brain, and also to put information into the brain. Before Neuralink, I was at UC Berkeley, where I co-invented NeuralDust, which is a technology to power and communicate with small implantable systems using ultrasound waves. Typical chip lifecycle from design to verification to tape out is approximately 1 to several years. At Neuralink, we had the ability to co-design our chip with the rest of the system, and the tight feedback loop from this organization has enabled our small team of analog and digital chip designers to tape out a new design every 3 months on average. That means over the past 24 months, we've done 8 tape outs in total, representing 15 different chips that have been designed, fabricated, tested, and used in development. The artwork that you see on the top of the slide is of some of the actual chips that we've made so far.
I believe a tape out is just referring to making a prototype of a chip. I'm imagining. So if they were able to do 15 chips, and it usually takes a year, if not more, they at least did 15 years of work that I guess a rather regular medical company would have actually done. So just another, I guess, why startup type fast iterative atmospheres and styles of work have kind of started to dominate the industry, being able to work a lot faster and a lot more iteratively than these slower companies, which is probably why Neuralink's going to zoom past a bunch of old medical companies and biotech firms that have been around for a while. So this next slide he has up, called the basic idea, and I believe he's going to describe how exactly it sounds like the electronics, but also kind of the algorithm in terms of it, how it all works. So there's a couple boxes that he shows. There's stimulation, electrodiagnostics, power management, analog to digital converters. So that's basically taking the actual spikes of electricity from the brain and then turning that into a digital signal. So just basically ones and zeros, and then being able to send that to a device. And then there's like a processing logic, which makes sense of it all. Analog amplifiers, obviously the individual electrical spikes from neurons are really small, so that message needs to be amplified for the electronics to read it. So there's a bunch of components. This is all just getting the information and the wavelengths from the brain into a digital signal and sending it to an electronic and processing it.
For any custom chips we make, the architecture can vary substantially, but the basic ideas are the same. Neural signals recorded from the electrode typically look like the one on the slide. And in order for us to extract the information that we care about, we need to first amplify, filter, and digitize those neural signals, and use digital logic to process and send out the bits we want for BMI. We also need ways to diagnose any issues with our electrodes and be able to drive Stimulation Engine to inject charge to the brain when required. Our latest chip is called N1 System on Chip, and it is physically small, measuring only 20 millimeters squared or 4 by 5 millimeters. It is low power, highly configurable, and it has 1,024 simultaneous record and stimulation-capable channels. And it has on-chip spike detection. To dive deeper into N1 SoC, I'd like to highlight 3 key innovations, and they are 1, analog pixel, 2, on-chip spike detection, and 3, stimulation on every channel. The first is analog pixel.
I believe the stimulation on pixel or on channel is when they're saying read to write. I think that's what he's referring to, but I'm sure he'll get to it. This first one, analog pixel, again, is what I touched upon, where the electrical signal comes into the amplifier. It throws it through a filter, which he's probably going to explain here, and then it converts that to all the ones and zeros for a digital signal. So the analog to digital converter.
Before we can convert analog neural signals into digital bits, we need to amplify and filter them. And this is where the analog pixel comes in. We want to have 1 analog pixel per electrode so that we can configure them independently. So in the case of N1 SoC, there are 1,024 analog pixels. Analog pixels also take up a significant portion of the physical space on the chip, and how well they work determines both the signal quality and the characteristics of the overall neural interface. The goal of analog pixel design is to make it as small as possible so we can fit more, as low power as possible so we generate less heat and have longer battery run times, and as low noise as possible so we get the best signals. Now, the challenge here is that these goals are at odds with each other. For example, we want to achieve lower noise on the amplifier so that more spikes can be detected. But as transistors get smaller, it becomes harder to get lower noise while keeping the power the same or less. Since the start of Neuralink, we've gone through 3 major revisions to the analog pixel, progressively improving both the size and power while maintaining performance. Over the past 24 months, we had 7-fold improvements in the size of the analog pixel, and our latest pixel on the right is at least 5 times smaller than the known state-of-the-art of similar architecture with 1 pixel dedicated per electrode, as published in the academic literature. Second innovation is on-chip spike detection. Once the signals are amplified, they're converted and digitized to zeros and ones by our on-chip analog-to-digital converters. As you'll hear in a second, spikes or action potentials shown on this slide are often critical for certain BMI tasks. Currently, there are several different methods for detecting spikes, such as thresholding, or more sophisticated methods such as principal component analysis. At Neuralink, one of the robust ways that we came up with is by directly characterizing the shape, and it's worth noting that this is different than template matching in that it gives us more information in a general way. In certain cases, we can actually identify different neurons from the same electrode based on their shapes. Our analog pixel can capture the entire neural signals sampled at 20,000 samples per second with 10 bits of resolution, resulting in over 200 megabits per second of neural data for each 1,024 channels that we record. In our previous systems that you heard about, we were able to stream this entire broadband signals through a single USB-C connector and cable, and we performed real-time spike detection on an 8-core machine running our optimized C code. Now, we wanted to completely eliminate connectors and cables for N1, so we had to modify our algorithms to fit into the hardware by scaling both, making it both scalable and also low power. And then we were able to also implement this algorithm in our N1 SoC. Our algorithms can compress neural data by more than 200 times, and it only takes 900 nanoseconds to compute, which is faster than the time it takes for the brain to realize it happened. Finally, it was important for us to enable stimulation from every channel that we can record from and make it configurable and high resolution. To make this work, we custom designed Stimulation Engine for electrical stimulation that can coexist alongside our analog pixels. Our Stimulation Engine has 0.2 microamp of amplitude resolution and 7.8 microsecond of time resolution. There is a 16:1 ratio of electrode to stimulation engine, so we can't stimulate every channel simultaneously, but we can within each stim pulse, usually in milliseconds, and we can also stimulate any combination of 64 channels at the same time. So in summary, looking through our N1 SoC, it has 1,024 analog pixels that we can record from simultaneously with 7.2 microvolt RMS noise while only consuming 6.6 microwatt of power. It has on-chip analog to digital converters, on-chip spike detection that can compress neural data more than 200 times, and it only takes 900 nanoseconds to compute. Stimulation engine with 0.2 microamp of amplitude and 7.8 microsecond of time resolution. And finally, diagnostics for electrode and impedance measurement. All of these functionalities that I outlined are integrated into a single 4x5 millimeter silicon die. Next, my colleague Flip will tell you more about what can be done with these signals.
Thanks, DJ. My name is Philip Sabis, and I'm the senior scientist at Neuralink. Before Neuralink, I was at UCSF, where I was a professor of physiology. There, for 16 years, I ran a lab that studied how the brain processes sensory and motor signals. We developed new neurotechnologies, and we studied how to take those tools and use them for neural engineering applications. Today, I'm going to tell you about how it is that we can use those amazing devices that Vanessa and DJ just told you about to communicate with the brain. Now, specifically, I want to tell you about two things. First, I want to show you that the work that we're doing doesn't come out of thin air. We're building on over a century of neuroscience research and decades of neural engineering research. These provide a solid foundation for the sorts of things that we're talking about. Second, I want to show you why we believe that even more advanced applications are possible with more advanced devices. Now, when Elon contacted me over 2.5 years ago now and told me about his vision for the company, I knew that I wanted to join for these two reasons. Because I knew that the technology was at a point where, with the right team and the right vision and a long-term vision, we could do the sorts of things that we're talking about. And I knew that with that team, we could do things that no one had even dreamed about yet. Okay. So the first thing I want to show you is a video. Many of you who are seeing this have seen videos like this before, so you know what it is. But if you don't know what this is, I have the distinct pleasure of telling you that right now what you're looking at is the brain at work.
So this is just a video of some EEG data coming through on basically one of the regular kind of graphs and charts that you would see. So there's just a bunch of kind of squiggly lines going left to right across the screen. That's all he's just showing right now.
This is in fact traces of a bunch of electrodes that came off of one of our devices, a bunch of electrodes from a single thread. And each trace shows you the voltage waveform in time as it's coming off of one of those threads. Now, if we focus in on one of those traces, the first thing you may notice is that there are these big voltage deflections that happen periodically, and these are the spikes that Max and Elon and others have talked about. These spikes occur, again, when a neuron has an action potential. And this is the fundamental element of communication within the brain, and this is the thing that we want to tap into. This is what we want to be able to record. Now, as DJ just told you, we have algorithms that can detect these spikes in real time as they're happening. And that allows us to collect data that looks something like this. This is what we call a spike raster. So each row there represents one channel of recording, and time goes from left to right. And each of those little tick marks is the time of a single spike in action potential. All right, so presumably there's some information somewhere in there. How do we get at it? What are we going to do with it? Well, for the first application, which Max told you about, which is allowing paralyzed individuals to be able to control a computer, what we want to do is we want to reach into primary motor cortex and record the activity that's happening there. Primary motor cortex is the part of the brain that sends signals down the spinal cord and to the muscles to drive movement. Of course, it does that with action potentials. And in particular, we want to record from the hand and arm portions of primary motor cortex. So imagine that you have a person sitting holding a mouse, and they're sitting still, and then they make an outward movement with their mouse, and then they reach back. What would you see in the brain? Well, here's a synthetic neuron. I made these data up, but it gives you the idea. Here's a synthetic neuron that shows that in the background activity, when the person's at rest, maybe there's some firing. But when that person reaches outward, that neuron starts to fire a lot. And when he reaches back, the neuron becomes quiet. So this is what we call a neuron that's tuned to a particular direction of movement. Now, maybe we'll record from another neuron, and this neuron may have a different pattern. It may be tuned to the return movement and not to the outward movement, so it fires more on the return. What if we ask the person to do that movement again? What we would see is a similar pattern of activation. So the neuron on top still fires more for outward movement, and the neuron on the bottom still fires more for the return movement. But you'll notice that the patterns are different. And that's because neural activity in the brain is random. It has stochasticity. Which means that even though the person may be intending to do the exact same thing from one movement to the next, the neural code, the neural representation at the level of an individual neuron is noisy. And this is just one of the reasons why we need to record from lots of neurons in order to be able to gain a high fidelity readout of what the intention is. So let's say we record from a bunch of neurons. It might look something like this. Now, if you look at that, you might think that looks pretty messy and it's not clear what's going on. But I'm going to do a little trick. I'm going to take those neurons and I'm going to rearrange them so that they're in the order of the tuning that they have, just as I told you about those two neurons. And if you do that, look what happens. Now suddenly structure emerges. And I think you'll agree, looking at that there's information in that stack of neurons that tells you about the movement. And that's exactly what we want to do. We want to do that kind of magic in an automated way to read out the movement. The way we do that is by building something that we call decoding algorithms. These are mathematical algorithms that we tune based on data like these to be able to take in just those rasters of spiking activity and output the movement that the person wants to make. Okay? So for these little fake data, I built a very, very simple decoder, and sure enough, it's able to capture the intended movement. This is what we want to do on a bigger scale. Now, you might say to yourself, I don't understand, you're talking about moving, but I thought it was about paralyzed people, right? So how does that work? Well, it turns out we know from a lot of prior research that even if you're not actually making the movement, even if you're just thinking about the movement, or even if you're watching someone else make movement, the cells in motor cortex respond in a similar way. So we can build up these decoding algorithms just from those kind of data. And then a paralyzed person can think about moving the mouse, and the cursor will move. Now,
I guess the question is what's the difference in the signal between thinking about doing something and actually trying to do it? If you have like a prosthetic and you're just thinking about moving your arm, you don't actually want to move it, how do you define the difference between those signals? Which is kind of interesting. I don't know if they actually know how to make the difference between those two. But what he was talking about with the spikes and the signals, basically there's a row, and every time there's a spike, there's just a tick, essentially. And when he rearranged all the signals and ordered them based on what movements they correspond to, there's an overall arching kind of wave of ticks that you can see through this whole graph. So that is what he's referring to, that you can actually extract some kind of pattern and data from this. And I think this is where the more prevalence and advancements in machine learning and AI is helping, because we can consume these massive amounts of data and actually extract patterns and do predictions out of them a lot faster than we would normally be capable of doing.
Sorry. This kind of decoding has been done in a fair number of academic labs, including my own before I came here, and in humans in academic studies. What we want, what Neuralink's goal, though, is to be able to do this with a clinical device that people can take home and use on their own, and that has orders of magnitude more channels, orders of magnitude more neurons that we're recording from. With that, we think that people will be able to get naturalistic control over their computers, not just a mouse, but also a keyboard, game controllers, and potentially other devices. That's what we're trying to do. Now, I've told you about the arm and hand area of motor cortex, but the devices that we're talking about, because of their high bandwidth and the ability to tailor the location of each individual electrode to a person's individualized cortical anatomy, we should be able to reach anywhere in motor cortex. So, for example, there are areas at the base of motor cortex that are responsible for driving activation of the speech articulators. There was a recent lovely study from UCSF that showed that from activity like that, you can actually decode speech. So you can decode the movement of the articulators, and from that, you can create synthetic speech. So potentially, with a device like this, you could restore speech to a paralyzed person who's no longer able to talk. But there's no reason in principle that we can't reach all of motor cortex. And that would give us access to any movement that a person thinks about, any movement at all. A person could imagine running or dancing or even kung fu, and we would be able to decode that signal. So that could give a paralyzed person the ability to control, say, for example, a 3D avatar that they could use for online gaming or sports. It could allow them to control a wide range of assistive robotic devices. And ultimately, if and when the technology for spinal cord, nerve, or muscle stimulation gets far enough, ultimately, it could be used to restore that individual's control of their own body. Okay. And I've talked about readout, but remember, we want bidirectional information. We don't only want to read information out of the brain, we want to be able to put it back into the brain. Now, to some of you, that may seem a little bit fantastical that you could write information into the brain. But actually, the basic building blocks of that technology are already there. This is the same image that you saw before of an electrode next to a cell. It turns out if you pass a tiny amount of current through that electrode, what happens is that you activate cells nearby. You cause them to fire an action potential, one or many. And that is the technology that is already being used widely outside the brain, say, for example, for cochlear implants, which have been used for decades to restore hearing to the deaf, and more recently, in the eye, to restore vision to the blind in a fairly rudimentary way, as I'll tell you more later. But in addition, you can use the same technology in the brain, for example, to restore the sense of touch or to restore vision. And I'm going to tell you very briefly about those two applications. So let's start with the sense of touch. Consider this little bit of tissue of brain that I've just highlighted here that's at the border between motor and somatosensory cortex. So if we blow that up, what you can see is that somatosensory cortex has a very special property. It has what we refer to as a spatial map. And what I mean by that is that there are regions that encode the palm of the hand and each of the 5 digits, for example. So if we were to stimulate at one little location, say in the thumb part of the cortex, the person would feel a sense of touch or pressure on their thumb. Or if we were to stimulate 2 sites in the palm area of cortex, you might feel a couple of points or touches on your hand. This kind of technology has been demonstrated in many academic labs. And in a recent really nice paper, it was shown that with subjects controlling a robot arm through BMI, getting tactile feedback of when that arm or when the hand of that arm was grasping an object improved the ability to pick up and place objects with the robot. So this is the kind of thing that can really help decoding. So imagine what we could do if we were able to take our device and cover all of somatosensory cortex. We could give rich sensation of objects, of haptic feedback when you're manipulating objects. We could maybe feel different textures. But it's not just about improving the user experience. It's also about getting to the level of functionality that we want. Imagine for a second, imagine typing. Now imagine typing with your fingers anesthetized. That's going to be pretty hard. So that haptic feedback, that sense of sensory feedback during movement is going to be important going forward. And yeah, okay. So that sensory feedback for the hand, we can also potentially provide visual feedback. So visual cortex, just like somatosensory.
I mean, the reason why this is all possible is just because everything you're experiencing is just everything you see, touch, smell. It's all your brain just interpreting it and like having these signals sent back to it from other organs. So if you could, let's say a particular organ like your skin doesn't work for touch, if this implant knew how to simulate what your skin would be sending back to you, then effectively it's restoring that function if you like don't have feeling for whatever reason. So this is what how they could essentially restore haptic feedback in someone's body, for instance, part of their body if they lost feeling in their hand or whatever.
The sensory cortex has maps. So there's a spatial map in visual cortex, which is here in orange in the back of the brain. So for example, if we stimulate a particular point in cortex, we might see a flash of light in a little punctate spot in front of us. And this was demonstrated many years ago by neurosurgeons, and it's been used in academic labs, and that we call that little dot a phosphene. And if you stimulate another area, you'll get a phosphene in a different location. So the idea here is that you could stimulate a bunch of different areas, and you could create kind of like a dot matrix image of the visual world, which could provide a rudimentary form of vision. And there are academic labs and even companies that are working on technology just like this. But there isn't just one map in visual cortex. Actually, there are a bunch of different maps. This is a good example of how the brain works. There's a spatial map, but there are also maps telling you about the orientation of edges in the field. There are maps telling you about color. There are maps telling you about the size and speed of objects moving. So what we want is a device that has sensors that are small enough, electrodes that are small enough, and a high enough density that we can tap into that rich collection of maps with our stimulation devices, so that we can do better than just dot matrix, so that we can actually create rich visual feedback for the blind. That's the long-term goal. Okay, that's just, again, one more example of the way that these devices can be used. So I've talked about recording signals, and I've talked about stimulating. You can combine those two to treat a variety of neurological disorders. Max talked earlier about deep brain stimulation to treat, say, for example, Parkinson's disease. And many people have those devices in. Academic labs have recently shown that you can do better with stimulation, you can treat better, if you also are able to record the state of the brain, say, from motor cortex, and use that to shape the pattern of stimulation. Deep brain stimulation, or DBS, has also been used for dystonia. It is already approved for dystonia and obsessive compulsive disorder. And we think, again, closed-loop therapies can do better. And in fact, for epilepsy, there's already a commercial product that does this kind of closed-loop seizure detection and disruption, although it does it with only about 8 electrodes. There are many other diseases. Oh, no. All right. We'll get there. Sorry. There are a number of other neurological disorders where DBS has promise, but is still an investigational stage, like depression, chronic pain, tinnitus. Now, even though these diseases are currently being treated with these big DBS electrodes like you've seen, we think that there's a potential here for the kinds of devices we're designing to get individualized, highly focused treatment that will reach broader patient populations and be able to be more effective in the way that they treat these disorders. All right, lastly, I want to tell you about not just sensory input and motor output, but about thought. So there are parts of the brain where we know that there's neural activity that encodes the things that you're thinking about. And one great example is an area called the hippocampus. The hippocampus is involved in memory formation, and it helps store episodic memory, things that you remember from your life. It also has a particular kind of memory for locations and views that you know. For example, it'll have cells that represent places in your own home or in a city that you know well. So imagine that you could record from a collection of neurons in the hippocampus of somebody who lived in San Francisco and knew it well. Then it's likely that they would have some neurons there in the hippocampus that represent various locations in Golden Gate Park. And so if that person were to take a car ride, for example, from the ocean through the park, you would see those neurons fire in order as they took that ride. First, a neuron that maybe represents a view of the ocean, and then the bison in their paddock, and so on. All right. So I've told you about the way that the brain represents information, and that these sorts of encoding methods, representations in the brain, are things that we can learn to decode. And I've told you about some of the applications and how they might work. As the device technology gets better and better, and as we get more and more experience with those devices, we and other researchers will be able to bootstrap off of those advances to reach other brain areas and other applications. That's what we're trying to do. Neuralink's goal is, neuroscience has shown that a wide variety of information content is readily available in the brain. We know, for example, that there are signals that encode speech and language. There are signals that encode your mood. There are signals that encode the sense of pain, when you're hungry and when you're thirsty. There are signals that encode your memories, and even esoteric things like mathematical reasoning. What Neuralink wants to do is to give people the ability to tap into those representations, to get better access to that information, both to repair broken brain circuits and also to ultimately give us better access to better connections to the world, to each other, and to ourselves.
Okay, so the rest of this video is basically just a Q&A that we're going to skip. But that's kind of the last speaker is one of the more interesting parts when he's talking about cognitive function and with the reading and writing. I mean, being able to decode and analyze mood based on your neural signals would be, I mean, you want to talk about emotional intelligence. You could basically have like an application that would read out exactly based on your neural signals what you're feeling, potentially based off that, or even being able to diagnose you straight up if you have clinical depression or whatever. So the applications of this are, it's exciting, and keep in mind they've only been working at this for 2 years. Mind you, they've, like he said, built on years of research for neuroscience and then the neural implants. But this is almost a year old now, so within the next year, so a year from now, we can get another 2-year update from them, and I'd be interested to see exactly how far they came in another 2 years. So I'll definitely try and keep up to date on any kind of information. They're pretty secretive. You don't really hear much about from Neuralink. But I do know that I actually have some guests coming on that are in the realm of neurotech, so they'll be able to kind of relay some information on what else is going on in the sphere, in the industry. And yeah, so thanks for listening again. If you haven't already, like, subscribe, all that good stuff for whatever platform. Leave a review for the podcast. And I might do another format, this kind of commentary stuff. If I could find, I wasn't able to find the video for the Cybertruck release, the Tesla launch event or unveiling rather, for the Cybertruck. But I'm going to try and see if I can get a hold